Bismillahirrahmanirrahim. Ladies and gentlemen, Assalamu alaikum and good morning. I am Asma Batul from Department of Computer Science and Information Technology, Virtual University of Pakistan. It is requested to please switch off your mobile phones. The audience is requested to please rise for national anthem. I would like to invite Mr. Hafiz Muhammad Azim Sarwar to recite few verses from the Holy Quran.
أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. يا أيها الذين آمنوا لا تلهكم أموالكم ولا أولادكم عن ذكر الله ومن يفعل ذلك فأولئك هم الخاسرون وأنفقوا مما رزقناكم من قبل أن يأتي أحدكم الموت فيقول رب لولا أخرتني إلى أجل قريب فأصدق وأكن من الصالحين ولن يؤخر الله نفسا إذا جاء أجلها والله خبير بما تعملون صدق الله العظيم.
Jazakallah. Today topic of talk is artificial neural network. This will enable the participants to give an understanding, usage, and importance of artificial neural networks in the current era and in future. This will also enable the postgraduate students to learn the methodologies used in advanced studies. Now I invite Honorable Guest Speaker, Dr. Farooq Alawi for his talk. Please come, sir.
Bismillahirrahmanirrahim. Rabbi shrah li sadri wa yassir li amri wahlul 'uqdatan min lisani yafqahu qawli. Assalamu alaikum. So this talk is essentially carrying on from the theme we put in place yesterday on high performance computing. A major application of high performance computing is exactly in this area of artificial neural nets, and we'll see in this talk how artificial neural nets are now essentially driving the entire AI revolution which has come into being in the last decade. So let me just see if this thing works. Yeah, it works. Okay. All right. So there are four subsections to this talk. So I'm going to start off by talking about a brief history of the neural paradigm and soft computing in particular. It's a way of doing computations for classes of problems which we cannot solve using traditional computational methods. All right. Okay. All right. Actually, the order here is unfortunately misplaced. This is actually going to be the second part, the second coming. I want to talk about artificial neural nets since the 1990s, because that was an era in which the current momentum for deep learning and all started to take root. And in the third part, we'll talk about the deep learning revolution itself. And then we'll go on and discuss what the applications are for now and for the future. Okay, all right. So let's start. Let me just ask. This is a master's level presentation. So if you have any questions, by all means, ask me. But it's going to be more instructive than yesterday's, which was more of a discussion, which at a professional seminar level. Okay, so I want to ask a simple question, everybody. How many of you can drive here? Okay, about half the people. What's the hardest part about driving? Backing the car. All right, reversing the car or parking, okay. So this is a classic problem which all human beings who can drive have to deal with, the car parking problems. And if you go to a professional driving school, they tell you that there are 4 steps you should follow in order to get your parking perfect, right? So what are these steps? First of all, align yourself. The mirror of your car should align with another car which is already parked on the road, right? Next thing is make a half turn of your wheel. The third one is, you see this line here, make sure that in your mirror that the number plate of the car behind you comes exactly in the middle. And in the fourth step, you basically put your foot on the pedal, and the car starts to reverse. And once you maneuver into that position which is vacant for you, you make the car straight. Okay, so this technique actually does work. Even my wife is able to park a car with this, right? So it does work. All right. We've heard of electric vehicles, right? Cars which can drive themselves. These cars have automatic parking modes built in. How does the Tesla do it? Tesla is the most famous electric vehicle car. So let's look at this video. Let's see how this car would do it. Okay, notice something, that the Tesla was unable to auto park itself in the first go. It started making move, then it had to go forward and reverse back. And the reason for that is very simple, that the start position of the car was in such a way that it was unable to come in exactly one single move. If you had parked it properly in the first instance, then of course it would have done it properly. Now, what is our expectation? Do we expect this automatic parking to be better than a human or not? What do people think? You expect it to be? It should be better, right? It should be, but in fact, it's not. People have done tests where they've timed themselves parking manually, and then they've timed a Tesla and other electrical vehicles doing it. And it turns out that quite often, about 50% of the time, the human is actually able to do it faster, right? And what does that tell you? It tells you that the human brain is still better than any machine that we can build, right? Experience, right? We can build machines, as we see in this lecture, which we can train, and the machines can learn from us, right? But there's nothing like the human brain. There just isn't. Okay, so the car parking problem, our observation is as follows. The final exact position, bearing, orientation of the car was not specified. Our goal here was just to be able to park the car in a given spot, right? We didn't care about, it should be pointing in this direction or that direction, it should be so many degrees from north or whatever. A trained human driver can park a car reasonably easily, and a trained electrical vehicle can do the same, sometimes with greater accuracy. Like I said, they've done tests where the human is able to outperform in speed on the parking problem. Okay, so the question is, what would happen if we attempted to park the car precisely down to millimeter precision? Is that even desirable? It's not. We're trying to solve this general problem here, right? We don't want millimeter accuracy. So perfection carries with it an unacceptable cost for human beings, right? That's a very profound statement, because it shows that we are not perfect as human beings, right? And we live in an imperfect world, and we are happy to live in an imperfect world, right? It doesn't really matter to us that the car is 100% aligned and parallel to the next car. It doesn't really matter. What matters is that the car is parked properly. And this lesson applies to all sorts of problems in your life, not just a car parking problem. Okay, so let's now proceed to a definition of what do we mean by soft computing. So first of all, let's look at hard computing, which is the computing that we are familiar with. Okay, so this is the traditional approach to computing. Here you develop algorithms with precise, provably correct exact steps. There are formal methods in mathematics where before you execute a program, you can write an algorithm and prove mathematically that it's going to work when you compile it. These methods do exist, right? So this is a very precise science. Okay. The other thing to notice is that traditional hard computing, as we call it, is deterministic. What do we mean by that? A deterministic system is one where no randomness is involved, right? The development of the future state is precisely identified given your existing state. So you know the steps, you know what you're starting with, you know the number of steps, and you know exactly where you will end up. And a deterministic model will always produce the same result from given initial conditions, right? So that makes life easy for us as programmers. Whenever you're designing an automatic system using a deterministic hard computing system, you know exactly where you're going to end up, because unless some kind of malfunction happens in the machine will follow your instructions precisely and give you the expected response. Compare that to soft computing, where algorithms are tolerant of imprecision, uncertainty, partial truth, and approximations. This is a non-deterministic system, and this is the kind of problem that the car parking problem was trying to solve. This was a soft computing problem. So who came up with this definition? This guy called Professor Lutfi Zadeh. He's the founder of Fuzzy Logic. So I think this was about 2 decades ago when he made this comment, this definition of soft computing. He said that, look, soft computing is not a single methodology, it's a whole series of technologies. It's a consortium of computing methodologies which collectively provide a foundation for the conception, design, deployment of intelligent systems. So he was trying to build intelligent systems. The reason that he came up with fuzzy logic was because he was trying to come up with imprecisions in knowledge and trying to solve the problem that he was working on. The principal members of soft computing are fuzzy logic, neurocomputing, genetic programming, and probabilistic computing. Okay, and the guiding principle is that soft computing is able to exploit the tolerance of imprecision, as we noticed. So here's an argument: soft rather than hard computing should be the foundation of AI. So based on what we have seen so far, does everybody agree with this? When we do artificial intelligence, we don't have to be 100% precise. Does that make sense? Yeah. What would happen if we had 100% precision? Same thing that would happen if you tried to park a car down to the millimeter level. You'd be struggling, for ages and ages just to get that precision, and it's not worth it. Right? Yesterday we had this comment about the law of diminishing returns. Right? There comes a point where the extra effort you put in does not give you better results, and that's exactly what's happening here. Okay, now it's also interesting to note. Again, going back to what we said yesterday, that, there's a philosophical angle to all these things that we do in engineering these days. And one of the philosophical things that we have to watch out for is the fact that, human behavior is imperfect. And there have been studies on this by all sorts of cultures. We know even from our Islamic culture that, mankind has been created weak, right? So we are imperfect, we know that. But, even Japanese culture has an entire theory about this. They call it the wabi-sabi. This is part of their Japanese Zen philosophy. And the Western culture also recognizes this. So there's this nice book, which is a bestseller on the New York bestseller list 10 years ago, which if you get a hand on, readers, it's quite a nice book. It tells you about the gifts of imperfection. Imperfection should not be seen as something to be avoided, but it should be embraced. It's actually good for us. Okay, so let's carry on to a classification of the technologies which are involved in soft computing based on what Lutfi said. So if you take soft computing as our root, we have biologically inspired computing and we have mathematical models, right? So Lutfi was working in this area. Fuzzy said that's where he began. Okay, but mathematically, another guy later came up with something called rough sets, which is basically a way of taking upper and lower bounds of set theory, right, and creating a whole mathematical model from there. Okay, as far as biology is concerned, we are inspired by two things. We are inspired by the brain, neural computing, and we are inspired by genetics, genetic algorithms. So our focus here today is on neural computing, right? But genetic algorithms themselves are an entirely big subject area, which I'm not going to touch on today. But that's also being used to solve all sorts of very, very difficult computational problems. Okay, so this is a slide which I hope to come back to later on. Basically, it shows you the historical development of neural networks, starting from the very first paper in 1943. So in 1943, we had this guy called, we had a team of two people, McCulloch and Pitts, and they wrote a paper on how neurons might work. And they created a mathematical model of it, which we'll consider in a lot of detail later on in this talk. Okay. In the 1950s, then, Rochester from IBM Research Labs, he had an effort to simulate neural networks. Then von Neumann, who is one of the key people in traditional hard computing, he also, he was working all sorts of various quantum mechanics to the nuclear program to whatnot. And he was interested in using neuron functions to analyze telegraphic relays for communication purposes. Okay, we come to 1950s, 1958, the guy called Rosenblatt, he began work on the perceptron. Now, the perceptron is again something we'll discuss later on in this lecture, but the perceptron was basically McCulloch and Pitts' mathematical model of the neuron. Okay, then we had the Dartmouth Summers research projects here in 1969, where artificial intelligence provided a boost to, this is around the first time in the 1960s when artificial intelligence began to be taken seriously as a subject. And it's very interesting that even back then, they were looking at neural nets as a way of solving these artificial intelligence problems. They had two approaches. They had artificial intelligence analytically done using neural networks, and then they had a storage problem that, look, you're collecting knowledge in artificial intelligence, just like the human brain. What do you do with this bunch of knowledge, right? How this huge database which is growing all the time? How do you access that knowledge intelligently? There are many ways of accessing knowledge from a database. People who've done SQL and whatnot, they know that there are these traditional methods. But what if the knowledge is fuzzy, like it is with humans, right? And you're happy enough with an approximate answer, then SQL is not going to work. You need a different approach. So there are these neural computing databases available now, which allow you access to large amounts of fuzzy knowledge and allow you to get approximate answers. And okay, then we had Donald Hebb. He wrote this book, The Organization of Behavior. Now, this was interesting because 1982, a lot of research in neural nets suddenly came to an end because of this book. When Hebb pointed out that there were certain classes of problems that traditional neural nets simply couldn't solve. So neural nets had to take a backseat because of this. For about 10 years, right? This doesn't mean that all work stopped. People like John Hebb and all, they still continue to work on it. But it wasn't around. It wasn't until around the late 1980s and early 1990s that interest in neural nets again began to spike. And the key development was this set of meetings between this competition between the Japanese and the Americans, when Japan decided that neural nets was going to be one of the ways in which they're going to leapfrog the Americans in computing power. So of course, when that happened, then the Americans jumped in as well, and they started collaborating with the Chinese, with the Japanese to combine their efforts. Okay. Well, there were mainframes and minis, right? I mean, remember from yesterday's talk, early 1980s, the IBM PC had already been launched in 1982. So desktop machines were already. Excuse me? No, they were slow. Yeah, I agree. But we had a whole generation of Intel's CPUs coming one after the other from the 8086. We went to the 286, the 386, which was like a radical. I agree. But again, mid 1980s, the classes of problems that they were trying to solve were not AI problems of the kind we have today, right? They were low-level problems of recognizing faces and stuff like that, which you can do even today on probably on your mobile device these days. Yeah. Okay. Okay. Yeah, so I mean, it's been uphill ever since, right? So 1980s, early 1990s is when this effort in neural nets research globally began to take a significant role. And the reason for that was, one of the reasons for that was that the European Union put a lot of effort into trying to build an artificial brain, as they called it, right? There was university in Jülich in Germany, which was behind this effort, and our team in England at that time was part of it. So I was involved with that as well. But they were trying to build an entire brain, and the project component given to us in England was one of looking at developing artificial neurons, which are very much like the human brain, but they are specified to solving the vision problem. We wanted to be able to see an image and recognize objects within that image. That was the problem we were looking at. Okay, so like I said, I'm going to hopefully come back to this now. So now let's move on to brain physiology, right? So we did say that this whole thing was inspired by biology, specifically the human brain. Okay, and what we have here is a very interesting diagram. It shows the brain from the top here, from the bottom, and from the side. Okay, and this is a cut through of the side image, right? This is a male human brain, not a female one. The female brain is different in some significant ways. On average, for a given age of a person, the female brain happens to be somewhat smaller, right? The other interesting thing is that you will notice that there are two halves of the brain, the right brain and the left brain, right? In a male human brain, only one side is working at a time. In a female, both can work simultaneously, parallel processing. Okay. This explains, by the way, why women can multitask better than men. Think about it, right? So women are more gifted than us. All right. The other thing to note is on this side here, we have the areas of specialization of the brain, because the brain is not just doing one thing, it does a whole bunch of things, right? What are the things it can do? It allows you to move your arms, your legs, right? Your whole body can move, your eyes can move, it has vision processing, it has the ability to hear and to interpret sounds, it has the ability to generate sounds from your mouth, etc. Okay. So I have here a list, I mean, you could read this in your own time, of which areas of the brain are specialized for which tasks. And again, if you compare the male human brain to the female human brain, some of these areas are different. And the most obvious one is the speech processing unit. In females, it's a lot bigger than it is for men. And that is why women are able to understand and communicate better than men are. Okay. Now let's drill down into this brain. So we looked at the brain as a whole structure, right? What if you took a microscope and actually started drilling down and seeing what's inside? So presumably everybody has heard that the brain is made up of neurons, right? These computational units called neurons. So what I have here is 2 videos. I'm going to run them simultaneously. And the idea is this. I hope there's audio today. The audio works. Yeah. So no, the audio. Yesterday, the audio was not working properly. So basically, this on the right-hand side, this video, right? This is taking some real images from the amygdala part of the brain. So I'll just go back here. Sorry. The amygdala is that part of the brain which is actually somewhere at the bottom here. Right? It's a small region of the brain which basically gives you your emotions and your fear. If you remove the amygdala from a person, they will not feel any fear. Okay, so it was one of the areas we studied as part of our Jülich collaboration. Now, in this part, what they've done is they've taken the amygdala, they've analyzed it, and then they have used those analysis pictures to generate a 3D computer model. And then they kind of fly and zoom around it to show you exactly how complex the neural structures are at that part. Meanwhile, on the left-hand side, we have basically a single neuron studied in depth, but there's no audio on this part, so I'm just going to start playing them, and you can see for yourself what they're saying.
Everything you see here is real data. We're looking through a microscope at neural tissue, going down through an area of the brain called the medial prefrontal cortex. We can use these microscopic images to reconstruct the 3-dimensional layout of the neurons and really see the intricate and intertwining patterns that they make. These connectivity patterns throughout the brain underlie all neural function and are responsible for everything from controlling your muscles when you tie your shoes to how you feel about your family. Understanding these patterns is a massive ongoing project for neuroscientists everywhere and could lead to breakthroughs for everything from consciousness to depressive disorders and schizophrenia. In this example, we injected purple dye into a far distant brain region called the amygdala, which is largely where our emotions and feelings of fear are generated. Purple wires are axons, or connections, coming from the amygdala into this area. We've also used some recent advancements in genetic engineering to select only the neurons inside this region that connect to the amygdala and dye them green. By combining both the green and purple dyes, we're able to see the full circuit of connections, viewing both the neurons that connect to the amygdala and connections coming back in from the amygdala. The locations and patterns of the neural connections, called synapses, show us how heavily these two groups of neurons are connected. To help us start to understand the incredible complexity of these neural networks, we develop computational techniques that segment or isolate individual neurons. By isolating a neuron, we can measure its characteristics, like size, shape, how many branches it has, and what general type of neuron it is. This may not seem like much, but it's really important for understanding so much about the brain. For instance, we know that malnutrition, stress, and cognitive disorders can all change how these branches look, but there are so many details that we don't know. That's why we, as scientists, keep pushing the envelope. To tackle these very complicated questions, we're getting together and combining fields ranging from physics and biology to mathematics and computer science.
Okay. What we need to take away from this from this video is this: that the brain consists of large numbers. There are about 100 billion neurons in a healthy human adult on average, right? And these neurons are floating in, as we saw in this video here, floating in what appears to be space. It's not space. It's actually seawater. Surprisingly, if you take out the water from the brain and compare to seawater, it's pretty much identical. Okay. So we have neurons floating in seawater, and that's really what gives us everything to do with our consciousness, our ability to see and hear and everything. Quite remarkable. Okay. The other thing to notice is that, like I said, 100 billion neurons on average in a healthy human adult. The neurons are one of the few cells in the human body which do not regenerate. Every other cell in the body can regenerate, right? So, if you cut yourself, you find that, after a few days, you're healed. Even the heart muscle can regenerate, but not the neuron. And this explains why, after a certain age, when the neurons start dying out, they start dying out by the age of 19, by the way, at a pretty high rate. But because you have 100 billion of them, right, you're able to function for quite a bit longer than that. But once the neurons die out, they don't come back. Okay, and that's why you lose your mental faculties as you age. So, this kind of elimination of our capabilities is kind of built into us as a human being. Okay, so here's a schematic of what we saw in this video here. All right. So if you start to analyze this a typical human neuron, you find that it has three parts, and the first part is basically the nucleus here, where the information processing takes place. So this is the cell nucleus, right? And this cell is unlike the other cells of the human body. If you look at any picture of a human cell, right, it has a nucleus, it has a cell body, and platelets and all the other things, right? But none of them have a structure as complex as this, right? So what are these structures? In addition to the nucleus, you have these things, these little things sticking out, which are known as dendrites, right? And these are the information input pathways into the nucleus. Information comes in along the dendrites and gets fed into the nucleus, where some kind of information processing happens. And once that processing has completed, it needs to go out, exactly like a computer, right? Input comes in, data processing happens, and then you store results in your external RAM or your cache or whatever. Exactly the same thing is happening here, right? The output needs to go out to other neurons around, not to an external RAM, but because you're in this huge matrix of neurons, it has to go out to other neurons, which will do other things with that information. So once the cell has finished its information processing, it basically sends a spike, which is spike by spike, it's an analog signal, right? And I'll show you a diagram of that later on. That signal goes along the axons and ends up on these so-called synapses, which are the termination points for the output pathway, right? And once it had reached the synapse, then the signal has to find a way to enter the next neuron. How does that happen? It happens like this. So here we have a diagram of one neuron communicating with another neuron, right? So what have we got here? We've got the dendrites. Remember, the dendrites is where the information comes in. Information processing takes place here, and once the information is completed, it travels down here as a signal, right? And then these synapses of the first neuron are aligned to, they're not completely touching, but they're very, very close to the dendrites of the next neuron. And the dendrites of the next neuron here are where the inputs from the previous information processing travel here. The further processing takes place, and then the whole sequence then carries on with all the other neurons. Okay, so what happens at the synapse dendrite interface? What is the synapse dendrite interface? Is this little region here where the where the synapse of the preceding neuron comes very close to but not touches the dendrites of the next neuron. Okay, so once the signal has passed down the axon and reached the termination point, what it does is it triggers a release of sodium ions into the seawater around it. Okay, and that's what we're seeing here, that these are sodium ions, right, which are released from the preceding neuron. And once those neurons approach the dendrites of the next neuron, there's a little channel here which kind of opens up and allows these sodium ions to come inside. In other words, information is being fed from one neuron into the another via these little floating sodium ions. Think about this, right? Everything that we do is happening because of sodium ions floating around in seawater, right? Now, I did say that I would look at the signal which travels down the axon. So the signal is basically an electrical analog pulse like this. When there's nothing happening on the neural cell, this thing has what's known as a resting potential close to -60 or -70 millivolts, right? It's always stable around this, right? As soon as this bunch of sodium ions come in, right, they are positively charged, so they increase the voltage from -60, and you find this little spike. It spikes up to a maximum value, and the spike is proportional to how many of sodium ions have come in. And once the sodium ion flow has stopped, the positive voltage has been removed. It goes back here, and then stabilizes again at -60 volts. So this is known as a spike pulse. The spike pulse is basically the signal processing mechanism for one neuron to communicate with the next neuron. Okay, so this video goes through this entire sodium ion channel thing in a much more detailed way. So I'll play this now.
When an action potential reaches the synaptic terminal of the axon, it encounters a region called the synapse. Two neurons come close together but do not touch one another. A minuscule gap called the synaptic cleft separates the synaptic terminal of the first or presynaptic neuron from the dendrite or cell body of the second or postsynaptic neuron. The arrival of an action potential at the synaptic terminal causes the synaptic terminal to become positively charged and release neurotransmitters into the synaptic cleft. The neurotransmitters diffuse rapidly across the synaptic cleft and bind to receptors in the membrane of the dendrites or cell body of the postsynaptic cell. Each type of receptor in the postsynaptic membrane binds to a specific type of neurotransmitter, and after binding to a neurotransmitter, the receptor causes specific types of ion channels in the postsynaptic membrane to open. As ion channels are open, ions flow across the cell membrane of the postsynaptic neuron along their concentration gradients. This flow of ions into the postsynaptic neuron causes a postsynaptic potential, dendrites, or cell body. Depending on the channels open and the ions that flow in, synaptic potentials can be either excitatory, making the neuron less negative inside and more likely to fire an action potential, or inhibitory, making it more negative and less likely to fire. An excitatory postsynaptic potential is called an EPSP. An inhibitory postsynaptic potential is called an IPSP. A synapse that produces EPSPs in the postsynaptic cell is called an excitatory synapse. Synapse producing IPSPs is an inhibitory synapse. Postsynaptic potentials cannot travel far in the neuron. After a few millimeters at most, the ions leak back across the membrane and the signal is lost. However, postsynaptic potentials travel far enough to reach the cell body. They determine whether or not an action potential will be produced.
Okay, so something I did not mention earlier was this business about excitatory and inhibitory responses. That is basically got to do with the following. If I step back a bit. So in here, we talked about sodium ions, right? Now, what sodium ions do, they create a positive potential, right? But they're also potassium ions, and potassium ions do the exact opposite, right? They make it more negative rather than make it more positive. So you have an excitation in one case, and when there's sodium flowing, and then you have de-excitation or inhibition when potassium flows, right? And the reason for this is very simple. That in some cases you want to enable the human being to do something, so you have an excitatory response. In other instances, you don't want them to do something, so you have an inhibitory response. So that's kind of built in at the neuron level, our ability to choose right and wrong. Okay. I'm gonna.
Potential reaches the synaptic terminal of the axon. It encounters a region.
So here's a remarkable observation. It goes back to the comments we had yesterday. We talked yesterday about the competition between communications and computations. And we saw yesterday that when we build computers, digital computers, computation is where we put all our efforts in, and communication gets in the way of any useful data processing. Here it's exact opposite. Here everything, all the effort of the neuron is into this communication using these sodium and potassium ions and these channels. Okay. The actual processing ability of the neuron is very, very simple, extremely simple in compared to the communication. So here communication dominates, whereas in our computers, computation dominates. Okay, so let's now put all this together. Here's a physiological experiment. How does the brain make you laugh, right? So let's say you're presented with some funny image or some funny character, right? Which hopefully you recognize here, right? And the first thing that happens is that your sensors, in other words, your visual sensors and your auditory sensors, they pick up whatever this character is doing, okay? And they pass it on to the set of neurons in your brain. Okay, so the first thing that happens from the signals which are received by the visual sensors is basically it goes into the visual processing side of the brain, and there this question is answered: is this thing funny that I'm looking at? Same thing happens with the audio side, that you pick up some sound, it gets passed on to the audio processing part of the brain, and the question gets answered: is this speech that I'm listening to, is it funny, right? And then the thing goes through your memory system, where you create a bias. Now, if you've seen this character before, this memory system is likely to create an excitatory response because you know that this character is funny, right? So it's going to create an expectation in you that, oh yeah, I'm going to see something funny which will make me laugh, right? And that's what's known as a bias. There's a bias based on your previous information. If you've never seen this character before, this bias would not exist. So the whole information would go through the memory and say, oh, I've not seen anything yet, just move on to the next part, right? But because hopefully you've seen this guy before, right? So, okay, I'm expecting someone funny because I know this guy, he's funny, right? And then the set of all these neurons, they start firing. They started firing these pulses. And so you have neuron 1 firing, neuron 2 firing, et cetera, et cetera. So you see this sudden increase in the spike levels here. And that's because, something has been recognized here, right? So an excitement has set in, okay? So this is what's known as a spike train. It's a spike train of pulses, right? And the spike train of pulses only exists from a neuron when the neuron is doing some actual data processing task. And the end result is this, that once the expected response has been achieved, the brain then sends the signal to the rest of the body, okay, it's time for you to laugh, so you have a good laugh. Okay, so that's how the brain works. Now, how can we as engineers start to model this thing, right? This is where our creativity comes in. How can we model all this? So McCulloch and Pitts, way back in 1943, they came up with this thing called the perceptron, which was the first mathematical model of the neuron. Of course, back in 1943, we didn't have all these details of channels and sodium and potassium, but because that was done only in the 1970s or so, right? But they still knew enough to be able to come up with this model, which basically said that, look, we can model a neuron with this little computing device here, which has a set of inputs, right? So X1, X2, X3 is basically the axons from the previous neuron coming in and providing some kind of information into your existing neuron. Okay, and what they did was they said that, look, these values are restricted to 0 and 1, so they're binary. Okay, and it performs a computing function, and that computing function has to be some kind of addition, because that's exactly what happens in the real neuron. These electrical analog signals which are coming in are then actually summed to generate the output train. And then you basically generate an output which is also 0 and 1. Okay. So the main theoretical result here is that a synchronous collection simply means that, you know, these a collection of these neurons is operating in step one after the other. A synchronous collection of such units is a universal computing machine. They show this mathematically. McCulloch and Pitts, this was their big achievement. That given this very simple computing device, you wire them up in a certain architecture, and you can show that, you know, this thing can implement any Boolean function if the result is passed through a step function. So what's a step function? A step function is mathematically this. There's a mathematical definition. It basically says that the output when added gives you a number between 1 and 0. So that's the easy way of looking at it. But here's a graphical presentation of it. A step function actually does look like a step. It starts with 0. When the output is non-zero, it jumps to 1. Otherwise, it goes back to 0. So here's a rectangle function, pretty much the same thing. And there's a whole family of the step function and so-called threshold functions, which are used in modern neural nets. But this is the simplest one. All right. So let's now dive into these features of the perceptron. So we've already said that the perceptron is basically a summing machine. It takes a bunch of inputs which are 0 and 1, right? It adds them, and it adds them not just by taking X1 and X2 and X3, but it also assigns a number called a weight to them, right? What is the weight? Okay, so the weight is modeling something which basically goes back to the biological neuron. What do you think it is? We talked about excitatory and inhibitory responses, right? Okay, so some responses from a previous neuron will be excitatory, some will be inhibitory, some signals will be stronger, some will not be stronger, right? And that's what the weight is modeling. So the weight, again, tends to be a value between 0 and 1, right? If a signal coming in is strong, then, you know, you'll have a weight close to 1. If the signal coming in is weak, you'll have a weight close to 0. So that's all it's doing. Okay. And then we have the computational units and other, and we have the threshold sigma. We also have the bias. Now, the bias is basically exactly the bias we looked at earlier, where, you know, you recognize this image of this cartoon character, and because you expected something funny, so the, you know, the bias kicked in and said, okay, there's an expectation here, and that's what the bias is. So the bias is usually an input by itself, which is set to +1 in order to, you know, enforce something positive to happen. So that's what happened here. Yeah, so the bias is basically this +1 neuron, which is hardwired one. This never changes, right? Whereas these inputs can change, right? So if you have +1 input coming in, consider that to be a bias, which is forcing the neurons in a certain direction. Okay, so after the neuron was, the perceptron model was first developed, a few years later, somebody came up and said, oh, you said you're going to solve all these all these Boolean mathematical functions. It turns out that the XOR function cannot be modeled by the perceptron. Okay, so the XOR function, everybody who's engineering should know this, that, you know, basically one or the other or both know. So if both of your inputs are the if you get a 0. If they're different, you get a 1. That's XOR. Okay, and they solved it eventually by introducing this thing called layers. Instead of having just one set of perceptrons, you basically have one set which you call first layer. Then you have another set called layer 2. And with a 2-layer system like this, you can actually solve the XOR problem. You can actually model XOR. So again, perceptrons actually can do Boolean functions perfectly, as was expected. Okay, so if we can have 2 layers, we can also have multiple layers, right? And that's what this is, a multi-layer network. This created the pathway to modern neural networks. And here's an example of what a multi-layer perceptron system looks like. You have a bunch of input neurons here. You have a first layer, you have a second layer, you have a third layer, and then you have a summation output layer here. Okay. And this gives you a recipe to design an artificial neural network, ANN, for absolutely any problem that you wish to solve. Okay, so here's the steps that you would want to take. You design a network specific to your problem. You adjust the weights, which is basically the learning and the training. Remember, I said that the weights are there to model the excitatory and the inhibitory responses of the neuron with the data coming in. You adjust your thresholds and your biases because if you want the neuron to behave in a certain way, this is what happens. And you keep repeating this. This is an iterative process. You keep repeating this until the desired response is obtained. What we've just described here is learning and training. Okay, because we are showing an input to this system here. We are making some adjustments. We're going through this iterative learning loop until we get the desired output. So basically what you're doing is you've trained this neural network to do a particular task. And in fact, this diagram here is basically a set of chemical symbols. You'll recognize some of this pH value and whatnot, right? So this particular design was used to solve a chemical kinematics problem. Okay, so an artificial neural network is considered fully trained if its training and validation set vectors give the expected response. So the training set is basically once you build this architecture, right? You have a training set which has a set of known inputs and known outputs, and you run this iteratively through the system until the presentation of a known input gives the expected output every single time. So that's known as a training set. Then you have a validation set. Once you've trained the system with this training data, you throw that training data away. You get a whole bunch of different data called a validation set, right? Which is similar to the training data, but not exactly the same. And you run it again to see if it's going to catch, these small differences. And if it does that, if it passes the testing phase, if it passes the validation phase, then your neural network is fully trained and able to go out and solve real problems. Okay, so people have spent a lot of effort in trying to get these learning algorithms developed over the years. So I've got this is not an exhaustive list, right? But these are the most prominent ones. So we have these so-called unsupervised algorithms where you just create your neural networks, set up the iterative loop, and let the system learn by itself, right? You set up a loop to throw the input data in, and let the system learn from that input data. Then you have supervised, where basically you're comparing every single input and output to make sure that it's doing the right job. You also have self-supervised. Some neural networks can be designed in such a way that they can learn by themselves, right? Okay, and then you have reinforcement learning. So every time a neural network gives the right response, you kind of reward it, and if it gives the wrong response, you penalize it. Okay. And these learning algorithms have more mathematical exotic names like gradient descent and conjugate descent, etc. Okay, so here we'll do a little example of supervised learning. This is the most prominent and the most well-known of the supervised learning algorithms, known as backpropagation. So I'll start off by showing you this particular architecture here. This is a 3-layer artificial neural network. Okay. And we have 3 inputs we want to show it. We want to show a square to it, a circle, and a triangle. We want the system to be able to recognize these shapes, right? So what have we got? We have the input layer. We have these 2 hidden layers, and we have an output layer. And the output layer will be one of 3 inputs corresponding to one of these 3 outputs corresponding to the 3 inputs of the square, the circle, and the triangle. So in backpropagation, what happens is, first of all, it's supervised. So when you have a training set, you show the set of inputs to the system, you look at the output, and you compare them. And if the answer is completely wrong, then what you do is you propagate that error backwards through all the layers, and get the system to recognize that this is an error. Next time, don't make the same mistake. So I'll just show you the animation how that works. So we're going to take a circle first. This is our training data here. We take the circle and we pixelize it. Everything is a pixel here. So we have a 28 by 28 pixel, 784 pixels here, and we feed them into the input layer here, right? And they go through the hidden layers. This is known as the forward pass. So the system is now beginning to learn. And we initialize this with some random weights here. These numbers here are the random weights because you don't know the weights from the beginning, because remember, weights correspond to your learning. Okay, so now the next set of weights for the hidden layer are being initialized and trained here. And then finally, next set of weights. Again, remember these weights are initially randomized. Okay, and we get a value here which is 0.5, which is a reasonably good approximation, right? 0.5 means 50% of the time is going to get the right value. Okay, but 0.5 is not good enough. We want a higher prediction rate. We want a 90% or 100% prediction rate. So what do? We calculate the error from the observed output versus the expected output, and that's what this table is doing. And we notice that one of these values needs to go down two of them need to go down, the other needs to go up. And that error we then propagate backwards into the network and make it realize this mistake that, look, you made this error, next time make sure you do not make this mistake. Okay, so that's forward pass and a backward pass. So this basically is one loop of the iteration. You do this millions and millions of times until the network is able to get this perfectly right. Okay. All right. Okay. So we now come to the deep learning revolution. So this is the reason that we have artificial intelligence technology today. Deep learning revolution is basically a result of this one paper written by Professor Geoffrey Hinton at the University of Toronto in 2006. Here's his website. You can download the paper from there. And what he did was he said that, look, we've been working with neural nets with 10, maybe 20 layers. We need to do much more than that, right? So what he did was he said, let's look at the brain. Let's look, this is a vision problem which is being solved here, right? And the brain has all these parts at the back of the brain which are specialized for vision processing. It's not just one area, it's a whole bunch of, there are 7 areas which are specific just to vision in the human, right? So what they're doing here is they're basically looking at each one of these areas, trying to model each one of them as a separate network by itself. And each one of those networks is a multi-layer neural network by itself as well, okay? So here you have thousands and thousands of layers. And this is coming much closer to how the brain actually works. Remember, we said 100 billion neurons, they're organized in areas. And that's exactly what this model is doing. It's trying to organize hundreds and millions of neurons into thousands of layers to try and be as close to the brain as possible. So the closer you come to the brain, the more accurate is your result. And that's what deep learning is, right? It allows you to give extremely highly accurate answers to difficult questions that we can't solve otherwise. Okay. Deep learning has been the root, as I said, of artificial intelligence, but there's a whole series of technology which came out of it. So you have deep learning, and from that you have machine learning. Machine learning is basically an ability of a machine to learn using deep learning algorithms by itself. Okay, and then artificial intelligence is another level up from there. At the moment, so by early in early 2020s decade, we are seeing a whole bunch of new algorithms coming out to solve artificial intelligence problems, and some of these are some of the most important ones are mentioned here. So we have this thing called a generative adversarial nets, which is used in generating deepfakes. Everybody know what a deepfake is, right? A deepfake is basically taking the prime minister's face and putting it on some other human body and making it appear as real as possible. So or maybe taking his voice and making somebody else sound like him, right? That's what a deepfake is. It basically creates an artificial version of a human being, which is, depending on your point of view, is either good or bad. I think it's bad. Okay, then we have convolutional nets, which are used for very highly precise image processing tasks, such as figuring out supernova clusters and stuff, astronomy, recognizing these difficult to recognize things from telescopes. And we have recurrent nets, which are used for predictions, especially for time series predictions. And there's a whole bunch of other of them, but these are the most prominent ones. Okay, applications of ANN. Because this is supposed to be the decade of artificial intelligence, and we are just getting started in the decade, right? There's a whole bunch of applications that people want to look at and begin to solve. And here are two references that you can read in your own time. But just to look at this one here, the 5 ways that artificial intelligence will change your world by 2050. This is looking at 3 decades ahead. So we expect changes in the entertainment business over here, in the medicine, cybersecurity, vital tasks, transportation. But this is just an explanation. You can't look 3 years into the future, let alone 30 years, right? So we expect a lot more will happen. So is this good or bad, what we're doing here? What do people think? It's bad? Does it have any good sides to it? Can it have anything good? Yesterday, we talked about the importance of philosophers and ethics people being involved in anything we do in computers and engineering. See, here's another application of that. When you build these systems, just because you can build them does not mean that you should build them, right? And if you were to build them, make sure that you have an ethical component or a philosophical component. There's a very good quote from Stephen Hawking, who said this: it will either be the best thing that's ever happened or the worst. If we're not careful, it may well be the last thing that happens to us. If these machines become conscious, there's a lot of effort in building conscious machines. We are finished as a species, pretty much. Okay, so that's the end of talk. Now, I promised somebody quiz. Who was it? Was it you? Yeah. Okay. So I have the quiz, but I was told not to give it here. So I can show it to you. Okay. So we can give this to you later, and you can pass it on. Yeah. All right. Okay. So any questions? Because this is like an MSc level talk. I'm happy to take questions. Welcome. So, that's a good question. Is there such a thing as an optimal number of hidden layers? It depends on various things. It depends firstly on the nature of the problem you're trying to solve. Okay, you have this technique called pruning. What does the word pruning means? It means cutting a tree. Okay, so what you do is if you start researching a problem where you don't know the optimal number of hidden layers, you always overestimate them. So if you think that the problem can be solved with 10, you start with 20, right? If it works fine with 20, great. Usually what will happen is you'll have something called overfitting that is giving better than expected results. And if that's the case, you start removing the layers one by one, and that's known as pruning, right? Until you come to the point where it's no longer giving the right results, and then where you've reached the optimal number of layers. So unfortunately, there's no other way of doing it. I think there are some people trying to solve this statistically, but I've not seen anything which suggests that they're successful.
There are two questions basically. First one is that ANNs are generally working for categorical classes or classification type of tasks. So what about linear type of outputs? Like we have linear regression type of methods. So should we implement these type of things like outputs class in this way that we have linear type of outputs?
Give me an example of a linear type of.
For example, if we are target layers like 1 to 100 or 1 to 1000 and 1 to million type of output. type of thing.
Right. Yeah. It can certainly tackle those problems. How accurately you do it, I don't know, because there are other techniques which will do the job perfectly for that linear class of problems. Why do you need a neural net for that? Because neural nets are computationally intensive. You need a lot of computing power for them. So if it's a straightforward linear problem, do it some other way.
As we know, ensemble learning, basically we have a lot of trees, and then we use voting method to compute the result. Like in decision trees, uh, we have tagging method and boosting method, in which we have a large number of trees. Then we can vote them by using voting method, that which type of output have most rows. Like in ensemble learning, we have 100 of trees. Each tree give output, and then we can vote them that how many trees give one and how many trees give zero. So in web Google, yesterday I learned the concept. How can we implement this type of thing? In how many ways should we adopt it to take the method in this way? We should implement this type of method, uh, like ensemble learning in artificial neural network.
I'm not sure I understand the question fully. You're talking about trees?
Yeah,
Uh,
like in trees, we have ensemble learning.
So you're trying to recognize some trees?
Yeah,
Okay.
in decision trees, we have a large number of decision trees, like in boosting algorithms or gradient boosting algorithms. We have 100 of trees, and each tree has given the output. Then we compute that how many trees given the right input.
Oh, okay. Yeah. That's a classic neural nets problem. Definitely. You can use image processing tasks. Convolutional neural nets are ideal for this. I talked about convolution nets for astronomy, but they can be used for this purpose quite easily. Yeah.
Assalamu alaikum, sir.
Well, so-
My question is regarding the basic structure of neuron. For example, when you said that a neuron takes input from dendrite side and it gives outputs at synapse, but this seems to be one-way relationship. For example, whenever a message passes to a brain, there is certain an output. For example, in terms of action. So how would the action terms flow? Yeah, I can repeat that. My question is regarding, for example, whenever a message is passed to brain, there is certainly an action in response. So the message passed as an input to dendrites and output is at synapse. What would be the returning sequence?
The returning sequence, okay. The returning sequence really depends on a macro view of things, right? What you're describing is the micro level of operation. Okay, depending on this is a human task that you're describing. Okay, so something is happening to the human in response to visual, audio inputs, whatever. You're looking at something and then you have to perform an action in response to that. Correct? Yeah. Okay, so that's the feedback loop. Okay, and it really depends on a whole bunch of different areas of the brain working together to address this issue. All right, so it's not just going to be one region. For instance, what's a good example? Let's say you in the middle of the night you hear some sound which you don't recognize and you're afraid. Okay, the amygdala kicks in, right? All right, what's going to be your feedback loop here? What is the likely set of steps that you would take in a situation like this? First of all, are you so afraid that you're not going to go and look for the source of the sound? And if you're not, you're brave enough to actually go and open the door and see what's happening, right? Then that means that you've suppressed the amygdala and you're using some other part of the brain, the curiosity part, right, to engage the world around you a bit more. And then you'll decide what happens after that. If there is danger, you do something. If there's no danger, you do something else. So it's different parts of brain interacting together. It's not just one little piece of the neuron with inputs and outputs.
Perfectly trained. How to validate our model is perfectly trained?
Yeah, there is a mathematical theory called cross-validation, which is used for that. I already gave you an example of validation sets, which is basically similar to the training set, but not exactly the same, right? And so once you've trained your neuron, you show a lot of validation data to it and make sure that it's performing. But there is a mathematical model cross-validation, which allows you to do this in a much more rigorous way.
So there is another question. What will be the optimal performance of the model? Like if we said that the model is overfitted, when the model will be overfitted? Like it's about 99% accuracy or it's about 95. What will be the threshold for overfitting?
Overfitting would mean that it does one part of the training much better than it does anything else, right? So interestingly, artificial neural nets can forget information. If you overfit, what happens is that one part of that of the weights is now having such values that it will automatically respond no matter what input you show. And previous information it may have seen of a weaker kind is simply ignored. So that's known as there's a word for it, I can't remember, but it's basically artificial neural nets can forget information just like the human brain can.
So 90 or 95 or 99%, what would be we set that threshold like?
Depends on the nature of the problem. Yeah, you can give an exact number like this and say that this always holds true. It doesn't.
If we have an image classification like problem or image object
yeah, but classification of what? Images, sound, what?
Object characterization, or for example, Asian or non-Asian classification. So if we have this type of problem,
yeah.
So at one time model will be overfitted, but when that's the issue. Like if we have 95% accuracy, like mostly deep learning models have high accuracy, given high accuracy as compared to machine learning models, because the data set in the deep learning models are relatively high. So when shall we train the model? When we left the training? When we left the training, like how much we train the model that it is not overfitted?
Oh, how long you should train?
Yeah.
Well, again, this is one of those questions for which no single answer exists. Basically, you train until you get the expected response, and supervised training is the best way of doing it, right? Okay. Another example would be this, that let me see if I can find the slide. Yeah, I'm not going to play the video, but what we are trying to do here is basically get this system to recognize the circle. Okay. Now, imagine that once this is fully trained, instead of showing it a full circle, I show it a wobbly circle, which is like hand-drawn circle. And if it recognizes that 95% of the time, is that overfitting or is that perfect?
I think it will be, it's not overfitted, I think.
Yeah, it's perfect. For instance, people are wearing masks these days, and yet you meet a familiar face, you know exactly who it is. Half the information is hidden. Why does that work? That's because your neural net, your brain, right, is perfectly trained for recognizing that one face, right? And that's exactly the example I gave here, that a perfect circle versus a hand-drawn circle. If the net is properly trained, it will still pick it up. That's not going to work for the simple reason, because then the system will be trained to pick up somebody with a mask only. If the original training set includes the mask, then it will be configured to do that. You're still able to recognize. Yes. You need only half of the information you need half the information in order to see the system operating the way you expect it to. But I wouldn't say that you need this in the training set. If you do that, you're building masks into the training data and therefore in the learning process.
Must be only one.
No, it doesn't have to be. But one is doesn't have to be.
So it is bias mean consciousness value or the stored value.
No, it's not. First of all, we can't really model consciousness. The one is there as a bias to force the net to behave in a certain way, right? So
It is the values that we
yeah, we as supervisors of the training, right? We are forcing the net to go in a certain direction. Giving it a bit of nudge. Want to do this rather than that.
where the consciousness values come. We say
No,
like we have trained the model and now we are using it for testing and it means we have added some values to it and it is a part of our conscious. It is a part of our conscious that if we are talking about that if the people are getting asked nowadays, but we still can recognize because we have met them before and
Yes.
we know them and it is a part of our conscious.
Yeah, I wouldn't use the word. I wouldn't see the word consciousness has a very specific meaning in this subject. Consciousness means be able to recognize oneself as a conscious human being.
It
We are
comes
self-aware.
in the when we are calculating or we are devising the algorithm. It comes in the calculation or not?
No, it doesn't. It's pretty much automatic. But the bias is there just to, like I said, to force a certain output. And it doesn't need to be there for all the field points that you solve it.
Assalamualaikum, sir.
Assalamualaikum.
I am Dr. Simon Naval. Actually, yesterday you talked about the higher performance computing. So which type of the higher performance computing should require for implementation of this deep learning applications and computations and implementation?
GPUs, basically. People are using GPUs quite heavily in neural nets because let's look at the equations we had earlier. The summation, right? The summation is basically multiply and add. That's what GPU does best. Okay, and there's millions and millions of them going on per second. So GPUs are used. FPGAs have been designed specifically for neural computations, and even some custom silicon.
Is GPU implemented in a cluster networks?
I know you are a physicist, but my question is more about biological thing. शायद वो सही से आंसर भी ना हो सके. But जब हमने एक स्पाइक देखा था कि जब भी कोई चीज अकर होती है तो उसकी वजह से एक स्पाइक आ रहा था. नॉर्मल वैल्यू से कुछ राइज हुआ था और जब वो वापस आया था तो नॉर्मल वैल्यू से भी नीचे चला गया था और फिर उसके बाद वो दोबारा नॉर्मल की तरफ आ रहा था. वो जो नॉर्मल से नीचे गया था उसको हम किस तरह से रिप्रेजेंट करेंगे या वो क्या है?
इसके लिए you have to think like a physicist, right? Because you're taking a certain value to a top. Think of instead of electrical, think of gravity, right? So you have a certain potential. You raise an object, increase the potential value, and you drop it. So it will have a certain momentum as it goes down until it stabilizes again. That's exactly the same thing which is happening. So it's really the momentum of the force of electricity.
And one more question. You said that there are positive sodium ions and negative potassium ions.
Yes.
But sodium and potassium belongs to the similar group, and the atoms lie in the similar group have similar properties. So, then how can a sodium have positive? It is very much fine. Sodium having positive. But how can potassium have negative?
I'm not a chemist, so I can't answer that. I mean, but you can see the wisdom in having sodium and potassium. So I think they are neighbors on the periodic table, aren't they?
Yes, they are in a similar group.
Right.
And the elements in the similar group have similar traits.
Okay. So they have similarity, but they have opposite charges.
Yes.
Okay. Yeah. So because I think it's also to do with the sizes of these ions. They have to be pretty small to go through the synapse, because synapse opens up a channel to allow them to flow. If the size of the atom was bigger, they might not flow, and then the whole thing would collapse.
Thank you.
So my question is about bias. So as we know, bias is a constant value that we input neural network. But how bias can affect the performance of the algorithm? Sir, as we know, bias is a constant value that we input our neural networks. My question is regarding bias. How bias can affect the performance of the algorithm?
How can bias affect the performance of the neural network? Yeah, first of all, what is the purpose of the bias?
Bias is a constant value.
It's a constant value for what reason? Because you're trying to push the network to behave in a certain way. Okay, right? So if you go back to the example we had of this comic character, and because you've seen the character before, there's a bias already present in your brain that there's an expectation of something funny to happen, right? And that's exactly what the bias value +1 is doing. It's kind of forcing the output into a certain way. Dr. Saab, I think there are no further questions.
Thank you very much, sir. This is the end of session. Please join us for the tea.